Welcome to this lesson 3 of non-equilibrium and stochastic processes. As usual, feel free to stop the video and reflect on what you are watching, maybe catching my errors. In these lessons, we shall move on approach that deals with the probability distribution, in particular Markov chains. We then inspect the Monte Carlo methods and how we can use computers in order to sample Markov chains and stochastic processes. Then we switch to continuous time processes and path integral approach and connections between statistical mechanics and quantum mechanics. So Markov chains are the fundamental topics of these lessons. They are essentially discrete time and discrete in state space stochastic processes that have no memory of the past. So the main point of Markov chain is that the probability of having something at the net time step does not depend on what happened before, but just on the present state. So we shall start with processes discrete in time and the state space. State space can be the position of a particle or some value that, I don't know, the sum of the people in a population or something like this. So let us consider a stochastic variable x of t, which can take a certain number of values. We can also have an infinite space, and time is discrete. So we indicate with the p of x and t the probability that x takes some value in this set at a certain time, and we can also call it pi of t. So essentially this probability distribution is nothing but a vector of generally large state space, but simply a vector. Clearly, each component of this vector are greater or equal to 0, their probability, and so the normalization implies that the sum of all the components of this vector is 1. The evolution of this vector is given by a conditional probability that we have already met in the past. So W is J. In this case, W for a finite set at least is just a matrix. So this is the probability of having x at time t plus 1 equal to Si. Remember that the target index is always the first, at least in physics, starting from a state j at time t. So this is the second index. Clearly, also W are probabilities, so all components should be, all elements of this matrix should be greater or equal to 0, and the summing on the column we should have 1, because it is a normalization of probability, essentially starting from J, in some place we have to go. And notice that in mathematics generally they used to write W with the index in the different in order. So in mathematics, Wij means W of probability of going from E to J, so that the normalization in this case occurs online. I prefer to use this notation because in this way we can just use the standard notation for multiplication, putting the probability distribution on the right, respect to what happens in mathematics, where they put the probability vector as a line vector, not a column vector, and on the left. Okay, so the evolution of the probability vector is this one, which is just a matrix multiplication, so that we can simply indicate like this. And so clearly the probability of distribution probability at time t is simply the power t of this Markov matrix time the distribution probability at time 0. So the matrix W normally is not symmetric, so it means that its eigenvalues are not necessarily real. Let us denote by W with the index k the right eigenvectors associated with the kth eigenvalue lambda k, so that this is the eigenvalue equation for the matrix. And we order the eigenvalues so that the first one is larger in absolute value because they can be complex, then the second, the third, and so on. Now, due to the constraints on P, essentially that sum I pi equal to 1, all eigenvector has to be smaller than 1 in absolute value, and at least 1 has to be 1, the conservation of probability. And in this case, or at least one, can be more. For those that for which the eigenvalue is equal to 1, all components are of the same sign, so they can be considered a probability distribution. Otherwise, just for being orthogonal one to the other, the sum of the component has to be 0. So some terminology: a state I is accessible from J if there is some time so that W raised to the power T component ij is greater than 0. Notice that it could be that the time t is different for different pairs. Even though all pairs are accessible, it may happen that not all are accessible at the same time. A state I is persistent if there is, say, a probability of coming back to this time equal to 1 to some power t. A Markov chain is irreducible if all pairs of states are accessible, maybe not at the same time, and it is periodic when the return times ti are all multiple of a period tau t, so that states are persistent, recurrent, if there is some time for which all return times are, so all states return all at the same time. This is called periodic. In order to take some confidence with the Markov chain, let us consider a very simple Markov chain of two states, say state 1 and state 2, so that I can multiply this on a vector p1 and p2, and this gives me the new vector. So you see that 1 minus q is the probability of remaining in state 1, 1 minus r is the probability of remaining in state 2, while q is the probability of going from state 1 to state 2, and r is the probability of going from state 2 to state 1. So let us call P1 of t the probability of finding the system in state 1 at time t. Clearly, P2 is 1 minus P1. And so we have this equation for the probability P1. So the P1 with the prime, I mean time t plus 1. So the probability 1 at time t plus 1 is the probability of staying there plus the probability of coming from the other state, and which is P2 1 minus P1. And so inserting the values there, we have this rate equation. And so this, we can find the solution for the stationary state, which is now for this is the solution for the in general for the state t, and so we have this equation, which is very simply the power of this matrix. So this is again the same equation. You see that if r equal q equal 0, nothing happens. If r equal q is equal 1, the system oscillates between states 1 and 2. Otherwise, if 1 minus q minus r is less than 1, asymptotically we have these two solutions here. And so the two states are both accessible and persistent. And if we want to to establish an equilibrium between the two states. It means that from state, if I compute the probability of being in state 1 times the probability of going into state 2, this should be equal to the probability of staying in state 2 times the probability of going in state 1. This is called the detailed balance condition, and actually it is obeyed by our asymptotic distribution. Now, next example is to consider a random walk on a ring with the periodic boundary conditions. So, particle can go in one direction or the other along the ring, only making one jump from one side to the other. So we have, you see, only the two diagonal near the main one different from zero, all the same with the periodic boundary conditions here. So W is a circulant matrix, means that every row and every column is obtained from the previous one simply by shifting. And so the evolution equation now is this one, and if we look to the stationary state, this is the condition, and you can see that at least one condition is that all p are this constant, all equal 1 over n. And the eigenvectors of W are the same as the all any circulant matrix, because all circulant matrix commutes with the shift operator, the operator that makes things shift by one position in a circular way. So this is the condition of periodicity of the shift. And so we integrating this equation for all the chain, coming back to number one, we found that the power n of the first component is 1. So W1 is the root of 1, so proportional to the complex exponential of 2 pi k over n times the imaginary unit I. And so this is the expression for all components. This is essentially this times j, and these are the bases of the eigenvectors of the shift operator. But since shift commutes with W, this is also the basis of the W matrix. And now we can find the eigenvalues of the W matrix simply by putting these eigenvectors into the equation. And so we find that the lambda k are given by this expression, and so it is a complex number, but nothing special. We have cosinus and sinus. So here again we have the expression for the eigenvalue of the work on the ring, and so you can notice that if you put k equal to 0, you have 1, so lambda 0 is equal to 1. If you take this modulus due to the presence of this 1 minus 2r, the all other eigenvalues have modulus less than 1, and so also that the components of the asymptotic state is asymptotic state with respect to the first eigenvalue are 1 over n, and and also that for r equal 1/2, it means that the random walk is symmetric, all eigenvalues are real. Clearly, if r is different from 1/2, we have essentially a collective motion that makes things to turn, and this is reflected by the fact of these complex eigenvalues. And clearly, if n is even the same as we have already seen for the one-dimensional random walk, odd sites at odd times cannot be in connection, so are always in connection with even sites at even time. So if we mix odd and even, there are the system decouples essentially into two non-interacting lattices. So essentially, if we consider a periodic boundary condition of say this goes here and this goes here, so and this is time, clearly this those that is here can only jump here and here, so it can never affect this, and so effectively all these sites marked with X only goes in these sites marked with X, and all these sites stay in a different sublattice. Clearly, this only happens if n is even. If it is odd, everything is connected. Oh, now we can put an absorbing barrier in some site. So here in state, you see that we have in state 1 what is called an absorbing state. It means that if you arrive in state 1, you don't exit anymore in this, while you still can go in state 1 essentially here and also here. I put a double barrier here in order, because n is can be even, so in order to be sure that we have an absorbing a boundary, for even all the odd number of sites, and so essentially this is again a problem of say absorbing, very very similar to what we have studied when we studied the random walk on two absorbing barriers. And so we have now two asymptotic state. The asymptotic distribution is either a delta on this first lattice, or a delta in this, or any combination of the two. So the asymptotic state is degenerate, and we have two eigenvalues equal to 1. So let us now study the probability that the walker that started at a given site j is absorbed in 1, and we call this probability P of j. And clearly, this probability obeys this equation here, because clearly, if it is absorbed from site j, but then it goes to site j plus 1, there is the probability of being absorbed starting from site j plus 1, and if it comes from site p j minus 1, we have to multiply this by the probability of being there times the probability of moving to site j. And so this is also putting the values of the rates, the probability of jumping formulated in this way, and we cannot use directly the solution that we have found before. The spectrum that we found for the shift operator is essentially the Fourier series. So this is clearly because anything which is periodic can be represented as the eigenvalue of the Fourier series. But nevertheless, we can try with this probability psi to some power j. So after some simplification, we get this equation, and this equation has two solutions. Phi psi 1 equal to 1 and psi 2 equal 1 over r over r, that we call S. So for r equal 1/2, the two solutions coincide, but in this case we have to find another solution, and we find the solution pj2 equal to j. This is the same as when we find a solution for linear differential equation. In the case where two solutions coincide, we have to find another one, normally linear solution. So the general combination is the general solution is a linear combination of the two. So for R different from 1/2, this, we have this combination with AS plus B equal to 1 and ASN plus B equal to 0. Inserting the two previous conditions means that if I start in 1, I'm immediately absorbed in 1, so probability is 1. If I start in n, I am absorbed in n, so I cannot be absorbed in 1. So we find that the constant A and B are given by these two expressions. So this is the general solution of being absorbed in 1 starting from site J. For n going to infinity and r greater than 1/2, s less than 1, we have a equal to 1 over s and b equal to 0. So this is how the probability of being absorbed in 1 becomes exponentially small with j, essentially because if I have r greater than 1/2, I have a drift, a bias towards n, and so clearly the probability of being absorbed in 1 becomes 0. Clearly, if r is less than 1/2, s is greater than 1, a equals 0, b equals 1, and the work is always absorbed in 1. For p equal 1/2, again, we have an intermediate solution. Now we have to use the other condition, the other solution, and I find a equal minus 1 over n minus 1 and b n over n minus 1, so that the pj has this form. And now having n going to infinity, putting j alpha n with alpha less between 0 and 1, it means essentially alpha measures the normalized distance from the trap. So pj is 1 minus alpha. So the walker has always a finite probability of being trapped in 1. Again, this is the same, an analogous result of what we have already found both for the mathematical theory of random walk and for our approach based on the Fokker-Planck equation. This problem, as anticipated, is called the gambler's ruin, since all games like roulette is designed to have a bias towards one of the boundary, which is less than 1. The boundary clearly are the trust you can raise, so how much money you can have. So essentially, you can expect to lose everything sooner or later. And so if we want, we just compute the probability starting with the capital of 500 euros, say, to lose everything with respect to doubling the capital, playing at fair roulette with a single zero. Single zero means that there is a drift towards 0, which is slightly less larger than 1/2, and so S, you see, is the drift, and so you can see that the probability of reaching losing everything starting from 500 is given by this. So essentially it is so now this is the probability of say yes, losing everything. So this is extremely vanishing, so certainly after 500 bets, one has almost certainly lost all the initial capital. Okay, now the point that is most interesting for statistical mechanics are ergodic Markov chains. So an ergodic Markov chain is irreducible, so the process cannot be split into two non-interacting processes. It is non-periodic, so it cannot come back to the same state ever and ever. And all states are persistent. It means that if you start from a given state, you can come back to the same state. And also every couple of states are connected with a certain finite probability given a large enough time. So the important point is that ergodic Markov chain has a unique stationary probability distribution corresponding to the eigenvector with eigenvalue equal to 1. This also means that we have just one eigenvalue equal to 1. And when you raise all the matrix M to some large value t, so M of t, and all the columns are the same and are all equal to the asymptotic distribution W of 0. So the Markov matrix at some power is simply the repetition of the stationary distribution. And this is obvious because you can start from a delta, so P0 can be just some delta in an arbitrary position, and MTP0 should go to the asymptotic distribution. So it means that multiplying this for this delta, you need to get the same distribution. And this is why the asymptotic structure of the Markov matrix is of the ergodic Markov matrix is this. Clearly, what is interesting is that changing some parameter, for instance, as we shall see in Monte Carlo computation, we can change the temperature, but there are out of equilibrium systems like a percolation theory in which you have some external parameter, for instance, the percolation probability, that changes, and this clearly it may happen that for finite system the system breaks into two, but this is trivial. The interesting point is when only in the limit n going to infinity the Markov chain breaks effectively into two disjoint matrices. So essentially becomes the matrix becomes something like a block matrix where we have a 1 MA, 1 here, 1 M2 here, and 0 here. And this means that there is a second eigenvalue that becomes 1, and this is essentially a phase transition in the language of Markov chains, which may happen also for systems which are not equivalent to equilibrium systems. So for instance, for which temperature is not defined or not the relevant parameter. There is an important lemma called the Katz lemma, and it's quite simple. The mean return time, it's the typical time that a walker takes to return to site J, starting from some other site. Clearly, in the limit t going to infinity, the starting point does not count. And so this is the definition of the mean return time. And essentially, the Katz lemma says that this return time is inversely proportional to the probability, asymptotic probability of staying in that site. Essentially, this you can see here a plot, and you see that if I take some reference point here, the time that takes to return to this point is very short if the probability of staying in this site is very large, because essentially we can so say that if a site is difficult to be reached, then the probability of staying there or finding the system there is small. Otherwise, if say site is central, so that any path crosses and passes through this point, then by taking something by chance, some sample, some interval by chance, it is quite easy to find the system there. And actually, the argument is this: consider a random walk and denote with the t entire jn the nth return time to j. So the total time needed to return m times to j is just the sum of these individual return times. The frequency is the inverse of the time spent at site I, is just the total number of return divided by the time needed for m return. But since wj of 0 corresponds to the fraction of time spent at j, in the limit m going to infinity, this is essentially the same. So w0 is the inverse of the return time. You can also say in another way, if you write down a typical sequence, no, say 3, 1, 2, 3, 4, 3, 2, 1, but we can also have jumps. So, for instance, we have 7, 5, 3, 3, 2, 1, 4, etc., etc., etc. And you count how many time you need to return to a given state tree. Then you can now make some some infield assumption so that you scramble this sequence, and clearly you find that the average time interval between two occurrences of the same symbol is essentially proportional to the total time divided by the number of these symbols. So essentially this result here. We can also analyze Markov chains by means of the spectral properties. So it is since the matrix is not symmetric, the eigenvalues, except the first, which is 1, are normally complex, and so the left eigenvectors are different from the right ones. But since we have this eigenvector equation that can be solved both for the left and the right eigenvector, we see that those two vectors are perpendicular if are properly normalized. So we can decompose an initial probability distribution P0 on the basis of the eigenvectors of W, assuming that there is not a generation, otherwise we have to be careful to take a basis, but not very complex, so that the P0 is can be written in using, for instance, the right eigenvalues W in this way, and clearly this is the expression for the coefficients of the development. And now if we iterate for a certain number of times the Markov process, we see that any time that we apply W to the eigenvector appears a power, so a factor of the corresponding eigenvalues. So at the end, since the modulus of all eigenvalues but the first is less than 1, this converges to the first eigenvalue. And since so we have proved that essentially if the Markov chain is ergodic, it has a unique probability distribution. And from the second eigenvalue, we can get the time, the characteristic time of convergence. And so you can also imagine here that if tuning some parameter, the second eigenvector second eigenvector W1 is going to converge to the first one, so becoming so not converging, but the second eigenvalues goes to 1. So this characteristic time diverges, and we have the equivalent of a critical slowing down in the phase in a transition of phase. So in order to appreciate the Markov processes, let us spend some words in considering Monte Carlo simulations and the role of detailed balance. So we can rewrite the Markov equation in the form of a master equation, the balance equation. So we take the difference from time t at t plus 1, we construct the difference, and this is essentially the equation for the probability flux. The stationary state is this one, which means 0 for the current here, and the sufficient condition that we have already seen is the Taylor balance, I mean the probability of staying in a certain state I times the, so the probability of being there times the probability of going to state J should be equal to the probability of staying of being there times the probability of going into the other state. And a Markov chain obeying the tail balance is reversible and ergodic, at least for a finite n. And this ergodicity, like in the asymmetric random walk that we have seen, does not imply reversibility. So the system can be ergodic but not reversible. And just a note that notice that we can use the tail balance to sample random numbers from an arbitrary distribution. So we have just to choose W such that the ratio between the two probability of passing from I to J is equal to the ratio of the desired asymptotic distribution. Then, if we find a Markov chain that obeys this condition, then the stationary distribution is the desired one. And this is a way of generating arbitrary the price distribution without using, say, throwing away too many random numbers. So in practice, we start from a sample J and we choose another target number I with an arbitrary probability Gij can be as we want at random or just the neighboring one or as you want. And we accept the movement with probability Wj that is taking in accordance with the tailed balance. So if J is symmetric, it disappears from the balance. So it is better to take this to sample to try to sample configuration in a symmetric way, and the statistic of the generated sequence converges to P. The problem clearly is how to choose I and how to implement the detailed balance condition. Clearly, if G covers all space, essentially we take I at random given J, we have what is called a direct sampling, which is clearly the simplest solution, but this is not really convenient in many cases. In particular, so if we have a limited domain, so a reasonable number of choices, then we can just take I at random. But what we generally have is that we may need to sample something from, say, 0 to infinity or minus infinity to infinity. Suppose we are simulating a gas and we want a velocity to take any arbitrary value from minus infinity to infinity. So it is not possible to uniformly cover an infinite interval with a given probability. And moreover, especially in statistical mechanics, we are interested in low temperature distributions, because the high temperature one is simple, as we have seen with the simulation of molecular dynamics. High energy configuration are those of an ideal gas, so any position is possible, any velocity is possible according to the Maxwell-Boltzmann distribution, and so it is not worth to perform a simulation. While we are interested in the crystalline phase, the liquid phase, so where the energy is low enough. But there are so many high energy configurations with respect to the low energy one. Generally, the entropy and the degeneracy grow with the energy. and so that if we take something at random, it is generally a high energy configuration. But if we want to perform a simulation at low T, uh, so what happens is that we have to refuse this movement, and so essentially we are throwing away computational time. So the generally acceptable solution can be not the best one, as we shall see, but one acceptable solution is to implement a G as an unbiased random walk by varying a configuration of a small amount. And this increases the acceptance rate. Remember that the ideal acceptance rate is about 50%, because if you want to sample something accepting or rejecting movement, every time that you make this movement, if the ratio of acceptance and rejection is about 50%, you gain 1/2 bit of information. So, otherwise, if you always reject or always accept, you are never increasing your estimation of the quantities you are interested in. So there are two well-known recipes for implementing Monte Carlo computation. So the Metropolis and the Hastings, Metropolis and Hastings one, or the heat bath solution. In the Metropolis, essentially, given I, you choose J, generally a small variation of I. For instance, you can take a particle and move it by a small amount, or you can take a spin and flip it, or something like this. If the probability increases, you accept the movement. Otherwise, you accept with a relative probability, which is the ratio of these two probabilities. Remember that these are the asymptotic probabilities. So you have to perform a random walk so that the average probability of finding this random walk in a certain position goes to your desired asymptotic distribution. So in order to implement this, you just extract a random number R from a uniform distribution in 0, 1, which is furnished by your preferred language by default. So by default, there are sometimes libraries, but it is quite easy to find the algorithm for generating pseudo-random numbers and uniformly distributed, and you accept only if this number is less than this ratio. And if the movement is not accepted, the particle stays there, but you you compute things as if it moved, because this is the rejection argument. Essentially, the idea is that, for instance, if you are performing a random walk in a square, it is difficult to arrive to a corner because you can only enter from two sides. But then every time you try to exit, you stay there because this is not acceptable. So you stay there long enough so that at the end the probability distribution is uniform, for instance, in this square. Another algorithm is the heat bath one. So given I, you generate all possible movement. Suppose that there are a certain number, and for instance, some of them can be staged just there, like when we do not accept the movement in the Metropolis algorithm, and another is the same as in the Metropolis one, and you choose one of them simply with the probability P of jk over the sum of this probability over all possibilities. So, for instance, you can just stay there because you choose the probability of P of I over the sum of over all other probabilities. So, in Monte Carlo, equilibrium statistical mechanics, you know the asymptotic distribution, which is the Boltzmann one, and H of S is the energy, and T, as usual, is the energy of the configuration. Z, as usual, is the partition function, so the normalization constant. So the problem is that finding a random walk that samples the space of all configuration with a frequency which is proportional to the asymptotic probability distribution we are looking for. Moreover, we are not really interested in computing the probability distribution because, in general, it has an enormous number of components. Suppose we are interested in computing the evolution of a system of n binary spins. So the number of components of P of S is 2 to the power n. So it can easily become enormous. Rather, we are interested in computing some average value of some observable. The idea is that we generate a configuration using the Monte Carlo approach, and then we sample them. Normally, we sample them when they are sufficiently uncorrelated so that we do not make errors in computing, for instance, the fluctuations of A. So we accept the replacement x into x prime with a certain probability, which is the minimum 1 if the energy, this is for instance for the metropolis computation, 1 if the energy increases, otherwise the exponential of the minus increase of the energy. And so we generate a fictitious time, so the time series where time it is a fictitious time, but it can be used also to sample some non-equilibrium property of the system, and then we compute the average value on this fictitious trajectory s of t generated by our Monte Carlo computation. And so, as I said, since successive configuration, if they are obtained by flipping, say, just one bit, are highly correlated, then we downsample the system. So we sample every n time where n is the size of a configuration. And if the Hamiltonian only contains local terms, so local couplings, like in the easy model, so most of the terms in H of S prime are equal to that in H of S that can be cancelled out. So essentially, we just compute the local variation of the energy. In order to be clear, let's try to derive the explicit Markov matrix for small 1D easy model, small in order to have a reasonable number of components of P. So we have to choose a configuration I given the present one. We read the configuration as a base 2 number, so this is the lowest bit and this is the highest bit. Really, in this representation, they are in the opposite as the normal order in a number. And so this is just for having a compact way of indicating a configuration. And the Hamiltonian is if we take 0, 1 instead of the usual minus 1, 1, the Hamiltonian can be written in this way, so that we have these minus 1, 1 effective terms using 0, 1 variables. So we rescale the coupling by the temperature. Since we are considering only one-dimensional Ising model with nearest neighbor interactions, we call the central cell C, the left one L, and the right one R. So the energy only depends locally on these values, and by putting into evidence the first term, we have this one, and So we can rescale the energy so that we only consider the number of equal or different pairs, and so this we also consider the variation of the energy when we flip the central cell, and this is the difference, so the code for the difference in the energy, and this is the we indicate by f of the two values the acceptance of this move, and so you see that for the metropolis 1 we see that we have 1 if energy decreases, exponential of the increase of the energy in the opposite skies case, but when we have 0 we can say flip things with a certain probability equal to 1/2, just to have some variation. For heat bath, things are more homogeneous since the probability is just given by this Fermi function, which can also be expressed using a hyperbolic tangent, which is something like this. And okay. Okay, so if we only consider 3 sites, here is the generic Markov chain for the central site, and clearly the Markov chain for the whole site is the product of 3 of them shifted in order to have the sites in the right position, and but the sequence of the update of the whole configuration is arbitrary. There is no recipe that forces us to use an order or another. We can simply flip the spin sequentially or at random. In this case, I choose to update the spin in sequentially so that we don't have to consider different possibilities of a random updating. And clearly, given the matrix that updates the central one, we can construct that, say, by performing the necessary variations of indices that flips the first or the third one. And so this is essentially the structure in general of the matrices, where all is the same but a certain site I, and so we can use the function f defined before, and finally this is for flipping a central site k, and so the total Markov matrix for the whole process is the product of in this case, if we use a sequential updating, of the probability of flipping sequentially all spins. So just to be concrete, for n equal to 3 and j equal to 1, and using the Metropolis algorithm, this is the matrix for flipping the central site. This is the matrix for flipping the first one, and this is the matrix for flipping the third one. You see that the numbers are always the same, only they are in different position. And so if we, clearly using MATLAB or other tools like this, you perform the product, you find that the Metropolis Markov matrix is this one, while the heat bath Markov matrix is this one. And you can see that they are not the same. They are not completely different, very similar, but they are, for instance, in some places they are either 0, and here you have the number different from 0, so they are not the same. Nevertheless, if you raise them to some high power, you see that, as anticipated, we have always the same distribution, clearly, except from numerical fluctuations. And these distributions are the same for the two systems. So essentially, they both converge to the same asymptotic distribution, and from according to the different cases, it may happen that one converges before the other. If we want to compare the asymptotic distribution, here I plot the distribution as a function of their index I. And so for a high t, means a low values of j, clearly the distribution is essentially flat. Increasing j, clearly we are in a one-dimensional Ising model with a small amount of sites, so we don't expect any phase transition, but at zero temperature, in which case we should only have a situation in which all spins are ones or all spins are zero, -1. And indeed, we can see that this is the case when we go to very, very small temperature. We have only two deltas, and the rest of configurations is here. And that's the trivial result. So even though in one dimension we don't have a phase transition for the Ising model, nevertheless, if we plot the value of the eigenvalues, the first one and the second one, as a function of j here, we see that the first one clearly is always a 1, both for Metropolis and for heat bath. Here we use a small lattice. But the second one converges to the first one, up to not being distinguishable in this graphic, for already for j equal 1.5, say, maybe for the heat bath there is no, essentially the same convergence. Notice that the two plots, even though they are quite similar, they are different. There are things that are different in the two systems. And clearly, if we had used this for computing two-dimensional systems, or if we apply this to system out of equilibrium, for instance, in the presence of absorbing states, we can appreciate this phase transition also in one dimension. So we may be interested in using Monte Carlo simulations to, for instance, check the results that we got in lesson number 1 using molecular dynamics. In this case, the energy is strictly conserved. In this case, using Monte Carlo simulation. So, as usual, we take our gas of particles. In this case, we are not interested in the velocity, since velocities, the expression of velocities into the energy is uncoupled from that opposition, so that the partition function can be factorized, partitioned in two. This means that the statistics of velocities is independent of the statistic of positions, but they use the same temperature. They are in thermal contact. So we can compute, and since the kinetic energies are the sum of kinetic energy for each particle, for each degrees of freedom, we already know that the asymptotic probability distribution of velocities is the Maxwell one, the Gaussian. So we don't consider velocity, which speeds up the simulation. We only consider position. So we can take one particle, move it of some amount in some direction, for instance here, compute the variation of energy, and if this variation is positive, we take a random number. If it is negative, we accept the movement. And so at the end, the gas explores the space at disposal. But actually, so we can calibrate this displacement in order to have an acceptance rate of about 0.5. But this is a simulation in the canonical ensemble. It means that we are actually keeping a temperature fixed and allow energy to fluctuate. We may be interested in performing a real microcanonical simulation. The problem is that given a configuration of particles, it is extremely difficult to find a movement that keeps the energy strictly fixed. In general, if you take a random move, energy can increase or decrease. It is not the same, so you have to diffuse the movement. In this case, you don't have a probability of acceptance. The acceptance is 1, provided that the movement conserves energy. So since it is difficult, the trick is to use one or more reservoir of energy. This is called the Kreutz algorithm, so that you accept the move if you can. For instance, suppose the energy decreases, then if you can store the excess of energy into this reservoir, or if the energy increases, if in the reservoir there is enough energy to be taken. Clearly, the size of the reservoir has to be small in order to limitate the fluctuation of energy around the average value that you want to maintain, large enough to accept a reasonable number of moves. And this is an algorithm which is interesting because it does not use random numbers for choosing to accept or not to accept the movement. Maybe only to decide which kind of movement in case of a gas. But for instance, if you use a spin system in which you can just flip things and maybe you update this in serially, then you don't have to extract any random number. This can speed up a lot the simulation, clearly, if you are interested in microcanonical simulations. You can also, for instance, cool the system down. Once that you equilibrated with one or more than this reservoir, you can void this reservoir and so lower the energy, extract energy from your system. This reservoir can be shared by all systems, or they can travel in the system so to quickly thermalize it. So there are a lot of tricks that have been used in the literature. We are not limited to canonical or microcanonical ensemble. Sometimes we want to be able to vary the number of particles. In particular, I remember having worked on a two-dimensional model of water, which is called the Mercedes-Benz model, because it uses units that resemble the Mercedes-Benz symbol. And this can simulate the crystalline state of water, which is this one, but you have to promote the formation of these voids here. And the problem is that when you strictly keep the number of particles, they can only bump or move but not disappear. So if you have a compact situation, it is not easy to have a hole to enter this sample. On the other hand, if you use grand canonical simulation, so you also allow particle to disappear to enter the system, it's quite easy to make holes. Clearly, in this case, you have to introduce also the chemical potential in order to control the number of particles in the same way as we control the energy using the temperature in the canonical ensemble. There are also possibilities of performing simulations in parallel for many sites. One is the cluster Monte Carlo, which is, so in general you cannot update things in parallel in Monte Carlo because when you compute the variation of energy of a given site, you have to keep all interacting sites in the same position, otherwise the computation is wrong. But if you can identify clusters of correlated spin, you can flip all them together. This has due to consideration that map the Ising model into a percolation model. Clearly, clusters are not just the site that happen to be in contact and have the same value of the spin, because since in the Ising model you only have two possibilities, say black and white, so you can have spins that happens to have the same value, even say at high temperature, where clusters should be quite small. So maybe the real cluster is this one, but you see a large bunch of spins that have the same value by chance. And so the algorithm is to take all sites that belong to that have the same value, but consider only links and accept these links with a probability which is connected to the coupling rescaled by the temperature. In this case, you identify the real cluster of spins and you can flip. The Svensson-Wang algorithm is the first that implemented this conjecture, this finding by Fortuin and others. And but the problem of Svensson and Wang is that they spend a lot of time building the clusters of spins. And so Wolf discovered the variation of this, stating that, okay, you just start from a random site. You build up the cluster of spins that are connected with the random cluster, and you flip it. And when you are in the high temperature phase, the clusters are small, so you flip them at random. You flip them, but they are built at random, so the final configuration is completely disordered. While when you are in the low temperature phase, you build up large cluster and you flip them with probability 1. And this means that if you, for instance, plot the magnetization with respect to time, even in the phase in which ergodicity is broken, so random walk should stay trapped into one valley, the Wolf algorithm continuously jumps from one of these valleys to the other one, because it has not to cross the energy barrier. And so, for instance, you see the magnetization continuously flipping from one value of the other. So essentially it is able to flip factorize the probability distribution in parallel. On the other hand, you can also use the standard single flip Monte Carlo updating, just having the care not to update spins that are that depends one of the other. So, for instance, suppose you have a two-dimensional system and you want to update sequentially in order not to waste time to generate random numbers all site. You cannot update really all site, but you can update a whole sublattice, this as a function of sites in the other sublattice, and then the other sublattice as a function of the first one. If the sides of the system, say call them L, is even, then the system really decouples into a pair of non-interacting lattices. And what can happen is that one of these lattices go in one state and the other go in the opposite direction, and so you have something similar to what happened using the Wolf algorithm, so that you may sample both branches of the factorized probability distribution at once. Notice that this algorithm is also nice because you can throw away completely one sublattice, so essentially identifying at even time one sublattice and odd times the other one, and so perform the updating in place, which can be quite useful. For instance, if you apply say multi-spin coding, so packing a lot of spin in the single computer words, and you don't want to duplicate the configuration. Okay, now just for finishing this lesson, let us consider the problem of continuous time stochastic process. Up to now, we have seen discrete time and discrete space processes, or discrete time and continuous space processes. Now, we still come back to the Chapman Kolmogorov condition that says essentially that the probability distribution in continuous time but discrete space conditions at time t plus delta t is the sum of the all intermediate state of the two processes. Essentially, this is again the like in random and path integral, you have to sum or to integrate over all possible conditions, intermediate conditions. Again, if delta t is small, jumps are also small, so that we can identify this transition matrix as something for E different from J proportional to the time and something different, so that the normalization condition now is this one here, and we find that the Chapman-Kolmogorov equation becomes the master equation that we have already seen in case of continuous time, so a balance of fluxes of transitions from one state to the other one. Notice that up to now we have not imposed that the jumps are limited. So for the probability that can be obtained by summing over the initial state, we again have a kind of initial a kind of master equation that again is similar to what we have got for the whole transition probability. And now, since we have mentioned many times path integral, let us do some consideration. So we start from the conditional probability that can be considered as a sum over all possible paths. For instance, let us consider a waltz on a lattice in order to have a standard reference. Again, we can call the probability p plus of going right and p minus of going left, clearly with the normalization condition, and we assume that they do not depend on the space nor on time. And so again, we can introduce the number of plus and minus steps, and as we have already seen for the mathematical random walk, the symmetric random walk, we can express the conditional probability in terms of number of the combination and the number of steps in plus or minus. So now, if we apply the Stirling approximation, we do not consider all terms as we did in the previous lesson, but we recover them by normalization. And so let us introduce, since we have the same problem that we needed to have odd or even times, so let us introduce these reduced indices so that this is the transition probability, and taking the logarithm, we obtain this number of terms. And if now we take we stay in the middle. In the middle means where the Bernoulli distribution can be approximated by a Gaussian, essentially. So we keep up to second order in time, in space, and we can perform some computation. Please check it. And so at the end, we find that the logarithm of w is equal to this expression here. And so essentially we have recovered the fact that the the probability computed at the sum over all possible paths behaves in this way like the solution of the diffusion equation, which again confirms all possible ways we have manipulated these things. But in general, we can write the probability as the sum of the initial probability times the um, the transition probability, and then this is the standard Kolmogorov formula integrating over all possible intermediate step, and if we move all integrals at the beginning, we recognize the appearance of a probability of a path. And this approach can also be useful to find a connection between quantum mechanics and statistical mechanics, because the formulation in a sense is very similar. Also in quantum mechanics we can say that in this case the complex amplitude of going from a point in the phase space position and time to another point in the phase space is due to the sum of all possible paths of the amplitude given to a path. But this is the same formulation that we have in probability, saying that if you want to go from some event A or some place A to some place B, and you have the opportunity of going by means of different paths, then you have to sum the probability, in this case for a classical probability, the probability of going through one path over all possible paths, and the probability of going from on one path is the probability of making single jumps. So we have two similar formulation. In quantum mechanics, you have to sum the amplitude, which is built by multiplying the amplitude for each small step, and then you compute the total amplitude, and then you take the square of the modulus, the square of the modulus of this amplitude, and this gives the probability. While in probabilistic processes, statistical mechanics, you just compute the probability. So, which is the relationship between these two formulations? So, so again, this is the description of quantum mechanics. You can see the Feynman-Gibbs book if you want a formulation of quantum mechanics starting from a path integral. So essentially, it says that the amplitude, which is a complex number, is the sum of the amplitude over all alternative paths. And the amplitude of a given path is this product of the amplitude for each step. Then we take the modulus of the square modulus of this amplitude, and this gives the probability. Now, clearly, since the amplitude is given by the integral of the action, the integral of the Lagrangian, which is the action for a given path, if you consider this essentially as the angle by which each complex number is rotated, you see that when you perform this amplitude, you have the square root of one possibility plus the square root, the square, not root, the square of the second possibility times the product that depends on the difference on the action between the two paths. Mm? And the action is the integral of the Laplacian, and the Laplacian is the kinetic energy minus the potential energy. Now, assume that we are in a flat space, so potentially is essentially constant, and also velocity is constant. We consider two paths with the same velocity. So that this difference in action is essentially given by this difference in potential, which essentially is zero, and this difference in kinetic energy. And so now clearly we can also introduce the de Broglie wavelength, and so essentially we see that this corresponds essentially to the difference in the path. So in a flat space, essentially the action is like a complex number whose phase is rotating at a constant velocity. So at the end, the difference in the phase is just the difference in the length of the two paths. And this is, for instance, what we expect for photons, since they always travel at constant velocity. Now, suppose that we perturb this one of the two paths, not the both, of something, we perturb the two paths of the same amount, but this gives nothing because this perturbation simply cancel out. But if we perturb just one of the path, this is like adding a number to this difference. Now, if the perturbation is stochastic, so we cannot simply perturb statically one of the path. It is like in an optical path to move one of the mirror. Okay, nothing happens. You can have interference or not interference, but nothing happens. But suppose you are vibrating or moving in a random way one of the mirrors, so you are altering in a stochastic way one of the part. When we average over it, because our measuring device is not measuring the single photon, or you can also measure the single photon, but when you want to see the interference pattern, you have to average over many photons. So you have to perform a computation over several replicas of our system, and then you see that essentially you can expect, say, an uniform distribution of this variation in a given interval, just to make things simpler, so that when we average this cosinus plus the perturbation term, we can factorize, and we see that actually when this perturbation is much larger than the wavelength of the system, this term vanishes, and so vanish all this term, and we recover the classical probability, for which you remember we are computing the square root of the absolute value of the amplitude, which was the square root of the first one plus the square root of the second plus the interference term. If the interference term goes away, you have just the sum of this, which is simply the sum of probability as in classical mechanics. So essentially, the message is that classical probability corresponds to quantum mechanics in a noisy environment, which is reasonable. It means that quantum mechanics rules always, but if you are in a noisy environment in which every path is perturbed by a stochastic amount. In average, you have a classical probability, classical statistical mechanics.